Assalamualaikum and hi. So this is the forced convection internal second video. So in this video I'm going to explain the entrance region for forced convection internal. The entrance region, velocity boundary layer or boundary layer. First we assume there is a flow with an average velocity v, and then it enters to the fluid into the pipe or tubes. First of the entrance we call the rotational core flow region, where the frictional effects are negligible and the velocity remains essentially constant in the radial direction. So the velocity is almost equal to the average velocity before it enters to the tube or pipes. And then we have the developing velocity profile, where frictional effect start to occur at the side of the wall. As you can see here, the profile start to develop. And then we have the fully developed velocity profile, which is in the parabolic shape. Here is the velocity profile is parabolic in laminar flow and much flatter or fuller in turbulent flow due to eddy motion and more vigorous mixings. And then at the bottom of this figure we have this hydrodynamic entrance region. This is the region from the pipe inlet to the point at which the velocity profile is fully, and the length is called the hydrodynamic entry length, LH. And after that, after the hydrodynamic entrance region, we have the hydrodynamically fully developed region, the region beyond the entrance region in which the velocity profile is fully developed and remains unchanged. As you can see here, delta u Rx over dx is equal to 0. This is the case for the hydrodynamically fully developed region, and the velocity profile is u is a function of ur. The hydrodynamic entrance region, delta u over delta x, is not constant. So please keep this in mind. And then the one I shaded with blue color is the boundary layer region, where the viscous effect and the velocity changes are significant. I put a note here. Flow in the entrance region is called hydrodynamically developing flow, since this is the region where the velocity profile develops. The entrance region, thermal boundary layer. So I already explained the velocity boundary layer. Now I'm going to explain the thermal boundary layer. So same with the velocity boundary layer, the profile also almost similar with the velocity boundary layer, but the terms is different. We have thermal entrance region, which is the region of flow over which the thermal boundary layer develops and reach the tube center. So the length is called the thermal entry length. And after the thermal entrance region, we have the thermally fully developed region, where the condition is delta x, delta of temperature difference, surface temperature minus temperature of the fluid, divided by surface temperature minus mean temperature of the fluid, equal to 0. Here is the region beyond the thermal entrance region, in which the dimensionless temperature profile remains unchanged. And the one that I shaded with blue color is the region called thermal boundary layer region, where the convection heat transfer from fluid to the tube wall are initiated. Thermally developing flow, flow in the thermal entrance region. This is the region where the temperature profile develops. And I put a note here. The fully developed flow, the region in which the flow is both hydrodynamically and thermally developed. So the boundary condition is delta u over delta x is equal to 0, and u is a function of ur, and delta over dx of the dimensionless temperature is equal to 0. Heat transfer coefficient and friction factor. As you can see in the figure, we have the H and F. H is the convection heat transfer and F is the friction factor, versus the distance starting from the entrance region to the fully developed flow for thermal boundary layer and also velocity boundary layer. And then we have two line, which is the Hx and Fx. Hx is the convection heat transfer, and Fx is the friction factor. And this is the region of the hydrodynamic entrance region, LH. And then we have the thermal entrance region, LT. We have the variation distance between these two. And then we have the hydrodynamically fully developed region. In the hydrodynamically fully developed region of a tube, the velocity profile remain unchanged and wall shear stress is constant. As you can see here, the friction factor Fx start to be constant at the hydrodynamically fully developed region. Thermally fully developed region. In the thermally fully developed region of a tube, the local convection coefficient is constant, does not vary with x. As you can see, starting at the thermally fully developed region line, the Hx, which is the convection heat transfer, turn out to be constant, which does not vary with the distance x. And here is the fully developed flow, which is both thermally fully developed region and hydrodynamically fully developed region in this region, and therefore both the friction, which is related to wall shear stress, and convection coefficient remain constant in the fully developed region of a tube. And as a note here, the pressure drop and heat flux are higher in the entrance region of a tube, and the effect of the entrance region is always to increase the average friction factor and heat transfer coefficient for the entire tube. Okay, as a note here, the temperature profile in thermally fully developed region may vary with x in the flow direction, and the dimensionless temperature profile defined previously remain unchanged. So in the thermally fully developed region, the dimensionless temperature remain unchanged when the surface temperature or surface heat flux remain constant. So please take note, in this forced convection for internal flow, we have two boundary condition, which is constant surface temperature or constant surface heat flux. So please keep this in mind. Okay, we already know the entrance region. Now we're going to calculate the entry length. So we have laminar flow and also turbulent flow for hydrodynamic and thermal. And you can see from this equation, we have slightly there is a variation in the equation that you need to use for each entry length. So please choose wisely for your exercise. Okay, turbulent flow Nusselt number. So as you can see here, we have the Nusselt number for, as I mentioned earlier in the notes, we have a constant surface temperature and also constant heat flux. So we plot it both of the Nusselt number versus the x over d here, and the line here is the Reynolds number. And as you can see here, the Nusselt number are much higher in the entrance region, and the Nusselt number reach constant value at assumed fully developed region, which is x over d larger than 10, and the Nusselt number for constant surface temperature and constant surface heat flux are identical in the fully developed region. As you can see, the solid line, pink solid line is the Nusselt number for constant surface temperature, and the dotted line, black dotted line, is the Nusselt number for constant surface heat flux. Okay, this is the end of second section for forced convection internal, and hope you guys enjoy this video, and thank you.